Radhe Radhe everyone. Today we're gonna discuss the solutions for the contest uh, 1070. I was able to solve 3 problems, although the problems were on easier side today. But let's go. Let's start with the first one. Okay, operations with inversions. Given an array from a1 to an, in one operation you can choose a pair of indices ij such that I is lesser than j and they are between 1 to n, and ai is greater than aj. So this is basically an inversion. And remove the elemental index j from the array. After that, the size of the array will decrease by 1 and the relative orders of element will not change. Determine the maximum number of operations that can be performed on the array if they are applied optimally. Okay. So what I'm saying is, or what the problem is saying is, if I have an array something like 10, 5 or a 2 and a 2, this is my array. So the problem is actually saying if my I is lesser than j and array of I is greater than array of j, then I could remove the jth element. Then I could remove the jth element. So if my I is this 0, 1, 2, so if my I is 0 and j is 1, right? So I is basically lesser than j and array of I is, as you can see, is greater than j. So what we can do is just remove this element, right? And then we'll be able to perform one operation. Again, if we compare 10 and 2, we'll see that now this array becomes something like this 10 and 2, and the ordering is just shifted by 1. And now you'll see that this condition still holds, that is I is lesser than j and array of I is greater than array of j, right? So now what we can do is just remove this element, and we were able to perform 2 operations on this array. So for this array we'll return 2 as the answer, right? So this problem is very easy if you are able to think about it. So let's have a 3, 2, 1, a 4, 5, let's say 6 here. So I'm saying let's just count the number of unique inversions, and then this will be it. What I mean by that is, if I have an array something like this, then if you see carefully, then if we fix I to be just 3, then I can remove this 2 and this 1, right? So we can perform 2 operations if we fix this I. Similarly, if we fix this 6, we know that we can remove this 3, remove this 2, remove this 1, remove this 4 and remove this 5, right? Because 6 is the greatest in this array, right? So if we fix this to be the I, then we can remove all these elements. So basically we will be able to perform n-1 operations, right? So I'm just saying, as n is pretty small, only up to 100, so I'm saying that fix I and then just run a second for loop from I plus 1 to n, and then if array of I or if a of I is greater than a of j, then just add this j to my set. Because if I write these indices, then if I fix this as my I, fix 0 as my I, so I could add 1, 2, 3, 4, 5 to my set, because they will form a valid inversion. So I added this to my set. Okay, and now we can remove this by maintaining this set. I could claim that I can remove these elements, right? And then we'll move on to the next I. So when we fix this to be or when we fix 3 to be my ith element, then we need to find all the elements right to it that are smaller than 3, right? So all the elements right to 3 which are smaller than 3 are 2 and 1, which are at position 2 and 3, and we can see that 2 and 3 are already taken here, so we do not want to take it. That's why we are maintaining a set here. And we can similarly do this for 2 as well. Check all the elements which are lesser than 2 to the right of 2, as only one is present which is lesser than 2 in the right of 2. This is present at index 3, which is already taken, so we don't want to take it. Similarly, we can do this for 1, for 4, for 5 as well. And at last we'll get the set, total set, that will contain the number of elements which are unique, which form a unique pair, or which form a unique inversion. So in this way we can remove all these elements by performing some operations, and the size of this set will be our answer, right? And that's it. This is it for the problem. Because if there's a valid inversion between, say, this I element and this j element, and then maybe this j is greater than some more elements, let's say these are some k elements, so j is actually, or a of j is greater than a of k elements. So what we can do is, first we can use this j to remove all these elements which are lesser than it, and then we can use this I to remove this j element, right? So we can see that all the valid inversions, or all the unique valid inversions, we can just take them into account into our set, and then we can just print the count of the set. So in our set, I'm storing j, that is the index of the smaller element, right? So that it should not repeat again. So 2 was lesser than 6, right? So this was coming with 6, so this was also coming with 3, right? So it should not be counted twice, because 2 can only be removed one side, either with 3 or either with 6, right? So I hope it is clear. The code is actually pretty simple. I got the first wrong answer because I was storing a of j to my set, not the j but a of j. So it might happen that I have something like this. So if I store a of j to my set, then I'll only get this one element, but indeed in this test case, we can remove this one and this one. So j should be unique, a of j can be repetitive, right? So yeah, this is the code for this problem, and that's it. Let's move on to the second one. You're given a binary string s1 to sn containing at least 1. You want to obtain a binary string of the same length consisting only of ones. To do this, you can perform the following operation any number of times. Choose a number d and consider the string t as a cyclic right shift of the string s by d, or more formally, t is equals to sn minus d plus 1 till sn, and then s1 up till n minus d. After that, for all j for which tj equals to 1, perform sj equals to 1. The described operation costs d coins, where d is the chosen shift amount. Note that the position j in the string s, where initially sj equals to 1, remain equals to 1 even if tj equals to 0. You need to determine the minimum number of coins that can be spent so that the string s consists only of ones after all the operations. So this problem is saying that, just a minute. So this problem is saying that I have a binary string s1 s2 up till sn, right, consisting of 0 or 1. This is a binary string. So the problem gives us there's at least one present in this string. So maybe we could have something like 0 0 0 1, right, or 1 0 1 0, something like this. So at least one has to be present in the string. That is what they're saying. Then they're saying that we could choose a number d, and then we can shift this string s by, we can cyclically shift this string s to the right by d places. So for example, this is my array. If I choose d equals to 1, and if I cyclically shift this right, so this element will actually come here, and then this will become 0 1 0 1 and 0, right? This will just come here, and this rest of the elements will be shifted by 1. Okay, so if I right shift this by 1, this becomes 0 1 0 1 0, something like this. If I choose d equals to 1 again, so this 0 goes basically here, so this becomes 0 0 1 0 1, right? So this is what they means when they say that we need to choose some integer d which can be from 1 to n, and consider the string t as a cyclic shift of the string s by d. So this we can call as t. If we choose some d and then cyclically shift right this string s, then we can call this the new string t. And then they're saying that after all, for all j for which tj equals to 1, you can set sj equals to 1. So let's take the above one example only. If I have a string like 0 0 1 0 1, then if I shift this by right, this will actually come here. So now our string t will become, this 1 will come before, so 1 0 0 1 0. And then they're saying that after that, for all j for which tj equals to 1, perform sj equals to 1. So they're saying that if tj equals to 1, then you should set sj equals to 1 as well, right? So tj equals to 1, you can set this as 1, and then this tj is also 1, so you can set this as 1 as well. So now my string, new string s would become 1 0 1 1 1, right? And then we can again right shift this by 1, and then we'll get this would actually go here, so this will be 1 1 0 1 1, right? And now we can see that this tj is 1, this was 0 initially, and then we can make this a 1, and then in two operations we were able to make this consist of only ones. They also say that sj equals to 1 remain equal to 1 even if tj equals to 0. So here tj was 0, but since sj was 1, this will continue to be 1, right? So we need to print the minimum number of coins that can be spent, so that the string s consists only of ones after all operations. So the general idea behind this problem is, if I have a string something like 1 0 0 0, I have only one 1, right, in the string s. So I'm saying that to make this string consist of all the ones, I will want to shift this right by 1, right? So now if I shift this right by 1, then my new string would become, this will actually go before, so my new string would become 0 1 0 0 0. And now you can see that this is actually set, this tj is set, so we will want to make this a 1, and then my new string would become, s would become 1 1 0 0 0, and now these three are remaining. So I could perform a shift right by 1 again, so this 0 will actually go here, and these will shift by 1, so my new t would be 0 1 1 0 0, right? You can see that this was 1, this was 1, this is cool, this was 1, this was 0, we'll leave it as it is, but this was 1 and this was 0, so we'll set this by 1 again, so my new string s would become 1 1 1 0 0. Similarly, we can again perform a right shift, cyclic right shift. This 0 would come here, this would become 0 1 1 1 0. This was set, we'll leave this as it is, this was set, this was set, this is set in tj, this is not set in s, so we'll set this, and we can do one more operation, and then we will be able to make this as 1 also. So you can see that if there are 4 zeros here, we needed to perform 4 operations. First one to set this 0, then we need to set this 0, then we need to set this 0, and at last we will want to set the last 0, this one, right? So I'm saying that the number of zeros the number of consecutive zeros will be the number of operations that I need to make this 1. So if I have an array like 1 0 0 0 0 1, right? If I have an array something like this, so when I right shift this array by 1, this is my s for example. So if I right shift this array by 1, so this will become cyclic. Shift cyclically right this by 1. So this 1 would come here. This will become 1 1 1, then 0 0 0 0, and a 1 0 0. So you can see that this one eventually goes one place to the right, this one eventually goes one place to the right as well, and this one also goes one place to the right as well. So I'm saying that if this one goes one place to the right in one operation, so for this subarray of 0 to become 1, this one will have to go 4 places to the right, in order to make this substring a 1, the complete substring consisting of 1, right? So first this 1 goes here in the first operation, we can see that. Then we'll set this by 1, we'll again then shift by this by 1. So now we'll be able to set this one. So this will cost me 4 operations or 4 coins. Similarly, this will again cost me 2 operations, right? So when this becomes 1, this also becomes 1. When this becomes 1, this also becomes 1, because essentially this 1 is shifting right by 1 in each operation, right? So don't you guys agree that if we have some array like this, then my answer would be the longest subarray consisting of 0, because essentially what is happening in each iteration, this 1 is getting shifted by right, this one is also getting shifted by right, and this one is also getting shifted by right. So I'm saying that the maximum number of consecutive zeros in my string is my final answer. So if I take 4, 2 and 4, the maximum is 4, and it will take 4 operations to make this string consist of only ones. So this is the general idea behind this problem. There is one more observation. So it might happen that this string could start with 0, right? So in that case, what we can do is, let's say this was my substring. So for this substring to become 1, we don't have anything left to it, right? If there was 1, if there was this 1 before these zeros, then this 1 would have shifted right. So this would have costed us 4 operations. But since there is no 1 here, so we'll need to borrow 1 from the last one, or the first one that we get when we iterate from the last. So this one will actually go to here in 2 operations. So in the first operation, this one will go this side, and since we are cyclically shifting right, cyclically means after this the last element, this then we actually go here, right? So we are actually shifting cyclically. So this one will go in one operation to the right, and in the other operation this will go to this element, and this element in the second operation would become 1. Similarly, in the third operation this would become 1, fourth operation this would become 1, and in the fifth operation this would become 1. So if I have an array, subarray or substring consists of zeros from the starting, then we'll need to find the first one when we iterate from the last, and then we can add these zeros that we encounter in my path, and then these zeros, and then this will we can just take the maximum of all such cases, right? So this is essentially it for the problem. This is the code. So my if my si equals to 0, I'm just doing a length plus plus. Then as soon as my si is 1, I could take the maximum of my current length of zeros, and then I could reinitialize this to be 0, and then I could just increment the I. In the case where where we need to handle this. I'll actually have my count of how many elements I encounter at the end, or how many zeros I encounter in the end. So I'll reset I equals to 0 and till si equals to 0 we'll keep iterating. So 0 1 2 3 4, so we'll keep iterating till si equals to 0, and as soon as we found a 1, we know that this is a substring that we want to convert to 1. So we'll add this length and then this length, right? So we can just take the maximum of that with my final answer. So I'll take the maximum whichever I was storing, take the max of max, or my answer, and then length plus I. Length would store the last, last number of zeros that I have, and then this I would give the number of zeros that I have initially, and then I could just print the maximum. So this is it. Let's move on to the third one, odd process. This was actually a very simple problem, but I took a little bit time to solve it because I wasn't able to prove the observation. But let's go. So you have n coins with the denominations from a1 to n and a natural number k. You also have a bag which is initially empty, where you can place coins. You need to perform exactly k actions. In each action you take one coin from those you have left and put it in your bag. After that you can no longer take that coin. So that means I can only take a coin once. At the same time, you have a cat that loves even numbers. So every time the sum of the denominations of the coin in your bag becomes even, your cat empties the bag, meaning it takes all the coins to a place known only to it, and the bag is empty again. Note that the bag is emptied every time the sum becomes even during the process of adding coins, not just at the very last moment. Let your score be the sum of the denominations of the coins in the bag. Your task is to perform k actions such that final score is maximized. So we need to maximize the final score that we get, and then they are defining the score as the sum of denominations of all the coins in the bags. Find the answer for all k from 1 to n. Okay. So basically this problem is saying that we need to perform k operations or k actions. In each action, we can choose any coin from a1 to an or from 1 to n, and then I could add that to my sum. Let's say or I could add that, I could pick this coin and take this into my bag. This was my bag. Now, if at any moment the sum of denominations of the coins in my bag becomes even. So let's say I've added a 3 and then I add a 3 again. So I add a coin with denomination 3 and then I add a coin again with the denomination 3. Then this becomes even. So that means in this case they are saying that there is a cat, and then this bag will actually become empty now. The cat will empty this bag, and now we have no coins, right? So this is the same as 0. So they are saying we need to perform k such operation. We need to pick k such coins, right? So they're saying that we need to pick k such coins. We need to perform k such operations, and we need to find the answer for all k from 1 to n. So first we'll find for k equals to 1, that is what happens, or what is the maximum score when we can only perform one action. Then what is the maximum score when we can perform 2 action? What is the maximum score when we can perform 3 action, right? So similarly and so on. So my claim is to prove this or to solve this problem, I want you guys to think in the direction that even plus even is always even, right? Odd plus odd is also even, right? But if we take a odd plus even or a even plus odd, then this actually remains odd, right? If you continue to add even further even elements to this will continue to be odd. So you can see that what would that be important, or how can we use this information to solve this problem? So I'm saying that since we need to maximize the end result, or maximize one minute, maximize the sum of coins, sum of denominations of coins at the end, don't you guys agree that I could just pick the largest odd element, the largest odd element, the maximum odd element, and then I could take k minus 1 maximum even element. So this will always give me this optimal answer, the highest possible answers. Wouldn't you agree that if my k, let's say if my k was 5, so if my k was 5, then I'm saying that I need to perform 5 such actions. So I'm saying that if at any moment my sum of my coins of denominations, or sum of denominations of coins becomes even, then that counter of the bag becomes 0. So I will not want to waste any coins, right? I will want to keep the sum being odd. I will never want to make it even, because if it becomes even, then I will have wasted those coins, because those coins will get wasted, right? So I'm saying that if I want to perform k equals 5 actions, then I will pick one maximum odd element, and the rest should be even. Because if at the first action I take the maximum odd element, so this is odd, so the cat cannot do anything right now, right? So in the first operation I take a odd element. So now that is also what I said here, right? So no matter how many even elements now I add to the sum, this will continue to be odd, because odd plus even is odd. Then again I add a even to that, so this will be odd again. So odd plus even is odd. If I add again a even, so this is odd again. If I add a even again, so this is odd again. So we can keep adding evens as long as we have those even elements, right? and these 4 even elements, or the remaining, so I'm saying 1 odd plus k minus 1 even, right? And this one odd element should be the maximum possible odd element, or the maximum possible available odd element, and these k minus 1 even elements should also be the maximum possible even elements, right? So in order to get the maximum possible k minus 1 even elements, we can just use a prefix sum over the reverse sorted even elements, right? So I could have this even elements array sorted in descending order, that is we could sort it in from bigger to lesser elements, and then we could create a prefix sum over that, right? So indeed in just O of 1 we can get the sum of k minus 1 even elements, right? The largest k minus 1 even elements for all k in order of 1. But now the problem comes that what if I do not have these k minus 1 even elements? So let's say my k was equals to 6, 1 2 3 4 5 6, then I'm saying that I need 1 odd and I need 5 even, and let's say my n equals to 9 and k equals to 5 or 6, so I need to pick 1 odd and the rest of them should be even. But I'm saying that in my array I only have 3 evens and then 6 odd. So what do you guys think we should do in those type of cases? So now I could only take 3 evens here, and note that if I take a odd element here, this whole thing becomes even. because the number of odd elements are now present even number of times. So odd and odd, this will become even, and then when I add even, so this will continue to be even, right? So the score will actually get minimized like this if I have 3 evens and 6 odds. So in that case, what we will do is we will just take we will just want to take as many even elements as I possibly can. So I want to take the maximum of, or the minimum, I'm sorry, the minimum of k minus 1 and total even number, right? So if total even elements are lesser than k minus 1, then we will want to take all the even elements, and if k minus the total number of even numbers are actually way bigger, so we can just take k minus 1 even elements, and I could just take an odd element. Also, one more thing, don't you guys agree that if we will not have any odd number, we will have array something like that, so in that case we will never be able to make anything except 0. So for all k in those cases, we will only be able to make a 0, because we have all the even elements in the array, right? We can do nothing about it. We will have to take even elements, and no matter how you add those even elements, we will only get a sum of even, right? So this is what I'm saying. Now this is the number of, I'm sorry, odd, or I'm sorry, this is the number of evens that I take for this particular k, and then rest would be odd. So this is k minus evens. Okay, so if my n was 9, we are just taking this sample. So if my n was 9 and my k was 6, so I need to in the best case I could select 1 odd and 5 even, but since I have what, 6 odd and 3 even, right? So I'm saying I could only select 3 evens. My evens become 3. So now my evens equals to 3, and then odd equals to k minus even. So 6 minus 3 is 3. So I want to take, I could take 3 maximum evens, and then I'll have to take 3 maximum odds, right? So since this odd was actually, the number of odd elements are actually odd here, so we will just leave it as it is. So this is, let's say we'll form an array like this, or we'll perform operations like this. We will take the any 2 odd elements, and then this will get a 0 here, right? Since k equals to 6, we can get a 0 here. If we group even number of odd elements, we'll get a 0 here, and then we can start forming our final answer like from here. We could take the maximum, this is the maximum odd element, and these 3 would be the maximum even elements, and now this will give me the final answer. And these are just dummy elements we are placing, so that this makes my sum even, right? If otherwise, if k would have been a 5, then in those cases evens would still be 3, but 5 minus 3 would be 2, so I need to take 2 odd elements, right? So in that case I will take 3 even element and 2 odd elements. But in that case, the number of odd elements is now even, so at the end my sum would become even, right? So if my sum at the end would become even, what I can do is I can remove this odd number, and I could add one more even number to here, right? So if I just remove this odd number and I add another even number here, so as soon as I perform this operation, the cat will actually make this 0, empty my bag, and then I could start from here again, and I could make this I could take my maximum odd number here, and I could take 3 maximum even numbers here, right? And I'll get my sum. So I just need to check if I have one even number that is remaining that I could take in order to form this, in order to maximize this part, right, the second part. So I need to have one even element, and I need to, I will want to remove this odd element. So I want to, have this odd element in order to remove it, right? So this is essentially it. You will understand better by seeing the code. So I'm creating even and odd arrays. I'm for creating those here. E is actually the size of even elements. O is actually the size of odd elements. This I don't know why I did. I was trying something else before, something similar. Then I'm sorting both the arrays. I'm creating a perfect sum of the even elements. I'm creating the perfect sum here in order to get the first or first whatever I need to get the first sum of even maximum even elements in order of 1, and then I'll check if odd doesn't, if I do not have any odd element in the array, then we'll have to get a 0, because then even plus even then would have been otherwise even as well. So now what I do is just ignore this answer for now. I can take the first k minus 1 to be my odd element, or I'm sorry, I could take this first k minus element, the biggest k minus elements, to be my even, and take 1 as to be my odd. But if j is equals to, j is greater than e, or in other words, if this j, these k minus 1 elements would have been greater than the number of even elements that I have, this e is nothing but the number of even elements, then I cannot take these k minus elements. I'll have to take the number of even elements that I have, right? So these are the number of even elements that I could take. Now I would give the number of odd elements that I could have. So I in this case is k minus j. So j was the number of even elements that I could take, and then this I was the number of odd elements that I could take. And now we saw that here, if the number of odd elements is even, then I would want to remove this one odd number, and I would want to add a even number to here, right? So this is what we're doing. If the number of odd number is even, then I will want to remove one even number, and then I want to add a one odd number here. Oh, I'm sorry, I will want to remove one even number, or I will want to remove one odd number. I will want to remove this odd number from here, and I will want to add one even number here. So I is actually giving me the even number, so I'll want to add a even number here, and I will want to subtract one odd number. So I'm checking if I haven't exhausted all the odd numbers. So if my j is greater than 0, and then my I is lesser than equals to or then this means that, I'm sorry, I'm actually getting confused here myself. So j is the number of even elements and I is the number of odd elements. So I'm saying that if the number of even elements is greater than equals to 0 in our sub array, in our k array size, right? So if my number of even elements is greater than 0, and if my taken number of odd elements is lesser than equals to O, or the total number of odd, then we can take the first greatest odd number, and then we can take the first for the maximum possible even numbers that I can take here. So j will give me the maximum number of even number that I can take. So I'll just get the prefix sum of that. So if I can take 10, 6, 4, 2, if I can take these 4 even numbers, then I would want to create a prefix sum 10, 16, 20, 22, and I will want to get this 22. So that is exactly what I'm doing here. I'm sorry, and I'm taking the maximum odd number. Otherwise, if my odd numbers would have became, or this I was giving the number of odd elements, so if my odd elements would have been greater than this odd, if in this case, I'm removing one odd and I'm adding one even, right? So I'm adding one even. This I is giving the total number of even, and I'm removing one odd. So I want to make sure that this actually doesn't become negative, right? So if in such a case where we would have only one odd element and rest would be even, something like that. So in such cases, if we remove this, then this complete thing becomes 0. So right, so that is what I'm checking, if I have only one odd element, and if I have removed that also, or if this becomes negative, the number of odd elements, or I'm sorry, if I'm actually getting confused here, I'm sorry. So if the number of odd elements because is actually lesser than equals to odd, total number of odd, because I'm actually adding odd here and I'm removing a even. Yeah, so I just explained the opposite of what I coded, but yeah, we can do anything we want. So if we would have something like odd and odd and then a even, so either you can remove this odd and add a even here, or essentially these are the same things. You have to swap one odd for one even, right? I'm saying that if you have odd number or if you have even number of odd, then the best option is just remove this the any dummy odd and then add any even number, right? So you can essentially do the opposite of it as well. You can add a j plus plus and do a I minus minus. So you can remove the one odd element and add one even element, or you can do the other thing as well. You can add an odd element. So essentially what you can do is you do not remove this odd, you keep them as it is, and instead of removing an odd, you remove a even from here. So we remove this and add a odd here. So this is the second case, right? So this will also give me 0. So I could have any two dummy elements here, and then this would be my maximum odd, and these will be my maximum even numbers, maximum two even numbers. So I could either remove this odd or I could either remove this even. So that is what I'm doing here. I'm actually removing a even over here. So I'm removing the one even number, I'm adding one odd number. And after performing this operation, I'm actually checking if this case is valid, then I'm taking the maximum odd and rest of them even, rest of the even whichever is possible, otherwise I'm outputting a 0. And this is just it for the problem. So I hope you got it. It's actually quite late for me, I would say, today, but I hope you liked my explanation. I actually tried to give my best. I hope you enjoyed it. I hope you got something new, and I'll see you guys tomorrow. I have something in my mind for planned for tomorrow, right? So yeah, we'll see. Radhe Radhe everyone. Good night and stay blessed.